Hello, and welcome to another episode of the Oxford MAT Livestream. I was having so much fun in chat, I almost forgot to go live. Good to have you with us, everyone. Have I got this switched on? I think I've got this switched on. There we go. I think I'm live to the internet. There we go. Everything seems to be plugged in. We are live and going. Yes, thank you, Nicholas. Hi to people in chat. Hi, people who have joined us over there in the Slido. Hi to Harriet and Raphael and Virat and some anonymous people as well. We're going to be talking about integration and differentiation today. I want to start with the poll because if I don't start with the poll, someone will ask for the poll, also because I want to do the poll. Hello to other people as well who are joining behind the poll. So as always, we're doing the quick vote for how was your day. I think people are now back to school. I saw in chat who said they were back to school. Adam said they were back, I think. And Carl said they were back yesterday. Kai, sorry, said they were back yesterday. Jack's here, Meeple's here, Mames Johnro is here. Adrian, hi to everyone. Shout outs. Carl Frederick Gauss turned up early. Good, right. Denim says, hi James, do you promise to not forget C today? I guess they mean the plus C on integrals. I'm going to try my hardest not to forget to add the C on those. Oh, they put a capital, Denim, you put capital C, which made me think that did I miss a capital C off something recently? You said it like it was an in-joke behind the C. Anyway, cool. Here we are then. Oh, people's day's going all right, 3.8, but there's a 10% on 1 star at the moment. And also, I am at about a 2 star, I think, so far. And I'm hoping that integration and differentiation for me today and to everyone else who's on 1 star and 2 star. Look at that 1 star peak. Oh my goodness. It's down there. Anyone else who's on a 1 star or 2 star day, I hope that the affirmation of doing a bit of maths and getting some things right is going to be helpful, I hope. Hi Johnny Valentine and Joe, who have just signed into chat as well. Let me mark this as good. Right, there we go. What's the average there? 3.7. That's a bit lower than we like. Only 33% 5 star. It's going down. Normally 5 star did a little bit better, I think. Right, we will see. Okay. Somebody voted for it just as I said that. Hooray, good. Okay, we will see. There's chat. Joe's here. Good. Okay. And I think I've got Prisma joining at some point soon. Oh my goodness. Look at this user. Is this going to show up on screen right? I think this may have... yes, this is showing up on screen just about right with the backwards J. Oh, I shouldn't encourage people really to do stuff like this. Let's do some integration. Should we do some integration? Let's see if it cheers me up. Right, cool. Here's the math syllabus of stuff you should know. People always like to ask me for integration on what else they're expected to be able to integrate, because at school you learn loads of other integration, either in the other half of Maths A level or in further maths. You learn just so much more integration, but this is the only bit that's in both the first half and in maths, so not further maths A level. So this is what I've got to work with for writing integration maths questions. Let's try and do one just to get going. And I think we're going to do a really hard one. I'm going to pick out the one from the thumbnail. This is 2014 and it's a question 1J. The short questions, we've said this before, the short questions are sort of slightly sorted, so that J is sometimes the hardest one out of the 10. Not always, and no promises, but occasionally we've tried to sort them out like that. And try, there we go, a little bit more central. Okay, here's the question. It's a bit horrible. We're told about this function f of x, and we're told that it satisfies this equation, 6 plus f of x equals 2 times f of minus x. Okay, so something to think about. This is for all real numbers x. Okay. Plus, and then here's the hard bit, 3x squared times some integral. And the integral is with respect to t, f of t from -1 to 1. This might be a little bit new, I suppose, a little bit strange. There's something going on here that this is the same thing as the integral from -1 to 1 of f of x dx. But they don't want to write that because then it would look like a function of x. I mean, it's not a function of x. It's also not a function of t, it's just a number, it's the area. So this is some number for the area. You could replace the t's or the x's with whatever you want instead. You could replace them with f of alpha d alpha, but that's a bit weird because alpha is normally used as a constant, so it just looks a bit strange. -1 to 1 of f of pi d pi, but pi is even more used as a constant, so that's probably a bad idea. Let's try f of You can even put your own symbols in. Maybe this makes you much more happy, because if you have your own symbol in here, you'll definitely not mistake it for an X or something else. I think I've tried to draw some sort of donkey or something in the box there. So if you want to replace all the pies with donkeys, then you can do that, just to make sure that they're not X's. They are something else entirely. But importantly, it's not a function of X, it's not a function of pi, it's not a function of donkeys. It's just some number. Good, right, okay. Good. I think Prisma's here, because chat is now running. There we go. Hands free. Thanks, Prisma. Good. Functional equations. Yeah, so in general, the study of these things with functional equations, like how Paul says in chat, in general, these are super hard. All we're actually asked for in this question is for that number, the integral from -1 to 1 of f of x dx, which is just, this is the same thing as this number in brackets. And we're not actually asked to solve for f, but to make the question a little bit harder, I think we can solve for f of x. We're not asked to, but I think we can. Let's try plugging in some values first. So often when you see, these are called functional equations sometimes, which is because they're equations and they've got functions in. It's true for all numbers x. We were told that somewhere just off the screen there. For all real numbers x. So in particular, it's true for things like 0, if x equals 0. I don't know if this is going to be helpful, but -0 is 0, and 3 times 0 is also 0 times, so I don't care. I've managed to kill off the horrible term over here. And maybe this is helpful, because I can now simplify this down, right? That's 0 times stuff, don't care. So f of 0 is equal to, what is that? Divide by 2, 3. That's kind of nice, I suppose. So we can extract this fact about the function f, without really engaging with all of the stuff in there. It's not helpful yet. Haven't yet worked out what f is doing. So maybe we need to try something different. So at some point, I think a sensible thing to do with this question, if you're doing this, if this is you in the MAT in 2014, then I think a sensible thing would be to call this area integral, to call this number a or something like that. Really is just some constant, and then you write out this expression with the a in it. But I think what I want to try doing is something a little bit different. Yeah, so I think what I want to try instead is something like, there's a method where you do that and then you rearrange f, and maybe you're already doing that. Is it 3? Is it not 3? It's 6, isn't it? Everyone's going to go 6. There we go. Sorry, thanks chat. 6. I divided by 2 for no reason. I forgot to subtract this one. Worst thing is that I stared at it for ages. Thanks Guy, thank you Meeple, thanks Jack, thanks Mames. Oh my goodness, how many people? Anonymous person, Vida, Harriet. Yeah. Problem with me not arranging chat is I'm also not always looking at chat, and then I can do something stupid and not notice. Thanks everyone. That never happened. 1 star. Down to 1 star. Okay. Could f of x have a constant in it? So f of 0 is not equal to 0. Yeah. So it could have a constant. In fact, it does. F of 0 is equal to 6. I don't know what it is. It could be 6 times cosine x. It could be 6 times e to the x. It could be loads of different things. It could be 6 plus some stuff. At the moment, I don't know. But I'm just sort of doing this to show you that you're allowed to plug in numbers. It's true for all real x, so you can plug in your favourite ones. Something I think I want to try next, I'm sort of avoiding the most direct way of doing the question, where we're trying to solve for this number a, really. You can plug it, if you call it a in this equation, you can do some stuff with that, like maybe do some integration. Something maybe fun is you can replace the x's with minus u. This is like a substitution or a change of variables. Those are quite technical ways of describing what I'm doing. I'm just going to replace all the x's with minus u's. This expression is true for all real numbers x, so it's also true for all real numbers negative u, because that's just a slightly fancier way of saying all real numbers. Not even fancy, just slightly mad. This is what it looks like when you do that. 2f of u plus 3. Now here's, if I guess, x squared, if x is minus u squares 2 minus u squared, that's u squared. And then this bit over here, this integral, just off the top of the screen there, this integral is still just f of t. There's no x's in there for me to replace with u's. It's not a function of x, it's just some number. Okay. Yeah, so Kai's asked in chat, if they put t for some reason, and t is something called a dummy variable, like my donkeys or my other examples of dummy variables, it gets integrated over, so it's not even really, the equation has nothing to do with t. If you put x's in here, it looks confusing because, okay, this says do the integral with respect to x, but when you read the equation, the x would be doing two different jobs. It's a bit like you could put the letter f in here, but it would be really confusing and weird, and don't do that. It's sort of like, it sort of doesn't matter what letter you put there, but best practice is to use a different letter for your dummy variable, just to emphasize that it's not the same thing as this x that's outside the brackets. When you come along with your favorite value of x, like 0, you put it in here and here, but you don't put it anywhere in here. You know, if you just write down x's, then you might accidentally copy this line out as integral of f of 0 to 0, but no, that's not what's going on at all. Okay, so to help people do substitutions accurately. Do you see where I'm going with this, by the way, at the bottom, where I've swapped? Yeah, don't do this, Adrian. Thanks for typing it. F of FDF. Oh my goodness. So what you've on today's episode, James is having a bad day and said "F you" to chat. Oh dear. I hope you see where I'm going with this. That I've replaced the x's with minus u's, and now I get a new relationship that's telling me it's telling me a slightly different fact about the relationship between f of u and f of minus u. I'm actually going to relabel the u's to x's. This looks confusing, I know, because we've already used x up the top, but I'm going to relabel them because I'm allowed to. Of this thing taking all of the different values, putting in all real numbers down here. So it's gone a little bit squashed, but we get this new statement out, which is very similar to our original statement, but the roles of f of x and f of minus x are a little bit different in this one. Yeah, please do not do. People are suggesting other terrible choices of dummy variable in chat, which is very off-putting. Rebels asked, do we know if they're odd or even? I think we're about to find out. We don't know yet. At the start, we know nothing about f, except that it does this. It satisfies this equation at the top for all values of x, for all real values of x. We're exploiting that a little bit by saying, well, it also holds if x is equal to minus u. We can put in negative numbers if you want to. That's one way of thinking of what we're doing here. You put in negative numbers, and the rule for if you put a negative number in here, then you see a positive number here, and the x squared doesn't really care. Okay, so in particular, I could put in like x equals 1, and there would be an f of 1 over here to deal with, and an f of minus 1. 3 times 1 squared. Or I could put in minus 1, and I would get f of minus 1 on the left, f of 1 on the right, and 3 times 1 squared over there. This is pretty good because I've now got two different expressions that relate together, f of x and f of minus x. I've got the one at the top, and I've got the one at the bottom. And I can subtract one from the other, I think. So if I take the top line and I subtract the bottom line, this is a different way of getting rid of the horrible integral term, because look, it's 3x squared times integral in both of them. So if I do the difference between this top line and this bottom line, this is going to go off the screen, I'm sorry, it's going to go down here. If I do the difference between those two lines, then I get f of x take away f of minus x is equal to 2 times f of minus x take away 2 times f of x. And then this 3x squared nonsense cancels out. Yeah, so u was standing for all real numbers, not always, but just in this particular problem, when I did this, I suppose x was any real number. So here u would be any real number. It's sort of like how they match up. You have to be a little bit careful when you do substitutions like this. I think you've probably been told to worry about squaring and things that happen when you do square roots and things like that. But just putting a minus sign, it's totally fine. It just takes all the real numbers and gives you back all the real numbers. Cool, what am I doing? I've got down to here, but this is a really simple expression that actually rearranges even more to say that f of minus x is equal to f of x. So Rebel asked, is this a even or odd function? And the answer has turned out to be this is an even function, if you know what that is. F of minus x is equal to f of x. Great news, really, really great. Because we now know that we only need to solve for what f's doing for positive values of x. Actually slightly better than that, and I'll show you in a moment. But this is another example of how you can be a little bit clever plugging in values of x. This time I plugged in a way I guess I plugged in all the negative values of x and all the positive values of x and used those to get between things. Line 2. So line 2 below f of 0 equals 6. Yeah, so this thing, request in chat. So this has come from taking the initial expression, which was true for all numbers, and saying it was also true if you, for some reason, decided to put in negative u as your number. This thing at the top is sort of true for any possible thing you plug in for x. It's true for f of minus 3 is 6 plus f of minus 3 is 2 times f of 3 plus 3 times 3 squared integral. And that's what I'm trying to express here, that if you put in negative numbers like this, it doesn't have to be a negative number, but you can think of it like that. If you put in negative numbers, then they kind of line up and you get a positive number over here. And then I've relabeled things to change the letter from a u to an x. Still true for all u, for all x. Goodness me. Yep, good. Okay. It doesn't matter if it's an odd or even function though, as the area is from -1 to 1. I think it matters a bit, right? If it's an odd function, the area from -1 to 1 is 0. If it's an even function, not necessarily. If it's an odd function, then this integral will be 0, and that's not one of the options. So, unfortunately, not all functions are even or odd otherwise. Anyway, what are we doing? I'm just messing around. I'm trying to solve for f because I want to. This is an amazing observation, really, for the problem, because if you've decided that f of minus x is equal to f of x, then you can just rearrange this expression. Look, this now just says you can subtract this. So if f of minus x is the same thing as f of x, then you can just subtract it, and you get a lovely expression that just says that f of x is equal to minus 6. Oh, moving this over here. No, just positive 6. Positive 6, take away 3x squared times this integral. I've still got to work out this integral. But maybe I'll just call it some number a for what this area is, and then just calculate from there and just plug everything back in again and see if I can work it out. Cool, right, that's one strategy which actually gives you the function itself, f of x. If we were trying to solve for what the function itself was, we would use that. Last bit that we need to do is actually calculate this integral. I've taken you off this way because I've taken you this way because what I want you to see is that sometimes you can do more than the question's asking. Sometimes there's more stuff going on. Some of my favourite questions have slightly more going on behind the scenes, where you can do slightly more maths than you're being asked to. This is not a good approach for the question, by the way. Probably not. Usually when we do this show, I'm showing you good approaches for getting to the answer quickly. Maybe not quickly. But here, I wanted to show you that you can do slightly better than the method I'm now going to show you. Okay, yeah, even though x is equal to minus u, yeah, okay. How am I going to get away with this? This sort of thing does annoy people a lot, doesn't it? So over here I said x was equal to minus u, and then I wanted to replace all the u's with x's. I can see how that's not, I can see how you're uncomfortable with that, because at one point I told you x was minus u, and then the next line, very next line, I relabeled everything. Yes, it doesn't imply that x is equal to u or that they're both 0 or something. There's something very subtle about the way that these statements are not just true for a specific number, they're true for all of the numbers. So there's something going on where really I'm changing how I'm describing all of the real numbers from line to line. And this replacement is just replacing the description. Instead of using the letter u, to use the letter x instead. I have a different thing you can write down if you like. So on the one hand, I could take my original statement. This is true for all numbers x. So in particular, it's also true if I change the x's to some other letter, like what's my favourite letter right now? A j. F of j is 2 times f of minus j plus 3j squared times the integral of stuff. So that's a true fact for all j. That's true for all j. And we proved that by setting x equals j. Okay, and if you believe the stop fact, then you believe this fact as well. I've just replaced x with the first letter of my name. But we have this other fact down here that's also true, the star line that I've been asked to explain. It's true for all values of u, so of course I can take that one as well, and I can replace that. I can replace all the u's with j's. To get this expression. So each of these lines are true, even though along the way it's true that I brought in this variable x is minus u to prove this one, and then I set u to be minus j to prove this one. Whereas in the proof for the first one, I just swap the x's to j's directly. I get different things out. There's no sort of version of the proof where you prove both of them and all the letters are consistent between the two proofs. But both of these lines over here are both true. I hope that makes slightly more sense. I know I've picked a weird letter of the alphabet. Nobody uses J for anything, which is a shame. But I hope that makes slightly more sense that if you believe the starred line, because I did x is minus u, and then I should be allowed to swap the u's to j's, right? Uncontroversial choice of letter, and this will be true. But definitely this first one's true, because it's just the same as the first thing that we've written down. Yeah, I've been called out for using j, which some people use as the square root of -1, so it's unhelpful. You can just change letters in your statements if it's true for all j, true for all of them. Or I suppose if you're talking about a specific one, then you can relabel what it's called, as long as you keep track. Okay, right, that was all in aid of trying to solve for quite a complicated way of solving for f of x. Let's actually do the question properly. Hi, welcome to the MAT Livestream. Here's a MAT question from 2014. It's question 1J, and the last one is usually the hardest one of the multiple choice questions, no promises. For this one, the thing you're supposed to realise is that this expression in brackets is just some constant. Let's call it a. Once we've called it a, we actually have something quite interesting, which is an expression, let's write it out, 6 plus f of x is equal to 2f of minus x plus 3a x squared. Here's the amazing idea. We could do something like integrate both sides. Because I don't really want facts about f of x. I want facts about the integral of f of x. Now, I know that's actually equal to a. It's the thing I've selected in the question and renamed as a. But what I can do is I can integrate both sides of this expression. I'm going to integrate both sides with respect to x. Okay, so this looks a little bit complicated, but bear with me. There we go. From -1 to 1, dx plus 3a integral of x squared from -1 to 1 dx. Over here, this is a rectangle with height 6 and width 2, so this is 12. This is the number a again, because it's the integral of f of x. This thing is also a, there's a 2 out the front, but this is also a, because all it's doing is reading the values of f reflected in the y-axis. The area underneath the curve is still the same after that reflection, so we're okay. And over here I've got to actually do an integral, but hopefully I can get through that. Good, that's looking okay. Slightly worried I'm not going to get one of the answers. Have I integrated correctly? 1/3, 2/3. Hit 2/3, get 4a, so I think solving that down, subtract an a over here, I think I get 2 more a's. So I think a is 4, so I think my answer is 4 at the end. Let me know in chat if it's going well or not. Cool, there's the fast version. Right. We didn't get to solve for what f of x is, and we didn't notice that there's an even function. But there's a fast version of just take your functional equation and try integrating both sides, having noticed that the hardest looking bit of the functional equation is actually the nicest, it's just a constant. Good, 6, 4, 6. Did I miss a dx? Probably. There's one in here. Everyone else in chat thinks it's 6, so that's bad news for me. Let's see if we can fix it. Oh, 2 1/3, 2/3. Bring it all back to me. 2a, 2/3, 2/3, 4, 3. I'm pretty sure I got this question wrong last year as well, so that's a fun thing. Some people got 4. No poll. Let's turn on the poll. Let's do the work. Let's do the vote. Let's do the vote. Let's try and solve this with dispute with voting. Well, SV's got 4 in both methods, so that's nice. And Ben's got an expression for what the function actually is, which is quite nice. I think so some people think I've lost an A. How's the voting going? At the moment, chat agrees with me, like a 90%. And actually, E is getting 23 is getting some votes. I don't know how you get to 23. D is picking up some votes. Oh, B is not that popular though in the actual voting. Cool, right, good. Why is everyone shouting 6? Loads of people got 4. I got 4. Chat got 4. Chat's converging on 4. Look, the votes for the other options are actually going down over time. Weird. Right, cool. Thank you, chat. I think we're gonna stick on 4. Solved it with democracy. Good. Sometimes I wonder if chat's just agreed to freak me out. You know, it wouldn't be that hard to coordinate, right? We'd just take like 2 or 3 people. Like that time everyone said the same whole number all at the same time. It was really bad. Right, good. How do you use the long version to get to A? The long version is great. It's gone and we restarted the entire show. But the long version is brilliant because you actually solve for f of x. After you've realised that f of x is an even function by manipulating stuff, you rearrange like this. So you get 6 on the left. I'm going to subtract an f of x from both sides. 2 times minus f of minus x is the same thing as f of x. I've got 3ax squared. Good. Okay, so I just need to work out that constant a. But I know the form of f of x. It's 6 minus 3ax squared. So if I integrate both sides of this, then on the left I'll get a from integrating it. Over here, I'll get the integral of 6, and on the right, I'll get the integral of x squared from minus 1 to 1. And I end up doing, I guess, the same sort of work. So this ends up being 3a is 12, so a is 4. So I think this ends up being f of x is 6 minus 12x squared. You don't need to solve for this, but hey, this is in the thumbnail, so I'm trying to do this. Yeah, 25 minutes to integrate both sides. Online lessons. The teacher would ask us to type our answers at the same time in chat, so people would usually just copy them and everyone would get the same wrong answer. It's a sort of convergence sort of thing, isn't it? Good times. Right, okay. Let's do the warm-up. I feel like we need the warm-up suddenly. And maybe some revision. I'm going to skim read the revision. Which sounds very dismissive of me, but I wrote it, so I'm allowed to dismiss it, I think. For math, you only need to know stuff that's essentially in year 12 mathematics. Quick list of what it is up here. This is in the MAT syllabus, which is on the MAT website. Link somewhere on screen to find the MAT syllabus, but hey, also literally on screen right now. You need to be able to differentiate powers of x, differentiate things like e to the kx. You need to know that if there's a fact number at the front, you can differentiate that, it's fine. Sum of derivatives, you're okay as well. You need to be able to find tangents and normals. The normal is the thing that's at right angles to the tangent. So your tangent might look like that. And your normal is the line that's at right angles. And we know a trick for curves that are at right angles, for lines that are at right angles to each other, so that's good. Things about turning points, zero derivative, look for your second derivatives to decide if things are local maxima or local minima or not. Things about increasing and decreasing functions. There's this thing that I think is taught in different ways in different places, maybe different bits of the world teach this very differently. There's an idea that differentiation, you can sort of understand it by having 2 points A and B on the curve, drawing in this is called the chord, the line between A and B, and then maybe moving B, think about moving B really close to A, and as you do that, this line segment gets closer and closer to being part of the tangent at A. The gradient of the chord gets closer to the gradient of the tangent line. Good. Oh, Zach, great news. The questions for next week's session were posted about a month ago. And indeed, the rest of the questions for the future sessions are already on the website. Link on screen for the MAT Livestream website, which just, there we go. Good. Oh, it's integration in the thumbnail, but also differentiation on the sheet. Surprise. We're learning about differentiation. Okay. Indefinite integration is the opposite of differentiation. So you can integrate things that, after you've differentiated them, you can integrate them to get pretty much back to where you started, plus a constant, didn't forget. We've got some integration facts over here, some things to do with how it's the area under the curve. Areas are positive for this. For Matt, I've sometimes used a different definition of area, but for now, if you're asked for the area, you're being asked for a positive number. And if your area is in two parts, if the region of the xy plane is in two parts, then you're supposed to split up your description of that area into two different bits, and then work out the positive areas of each of those. There's a different definition of area, which is a little bit weirder and would return, I think, 0 for this, something like 0 for this. It depends. If you believe that integrating around shapes in different directions should give you different answers, then you can define area in a slightly different way like that. But you run into the sort of problem that figure of 8 shapes like this have 0 area under this new definition, because they're kind of going round one way and round the other way on the other half. Anyway, other definitions of area also exist and are not relevant today, so they're getting erased. Today, areas are positive. Split down your region into different areas. Yeah, there we go. Good. Okay. Oh, Todo Wolf has asked, what happens when n equals 1? And this is -1. Thank you. Let's put it on the list of typos. I was just getting all excited and ready to talk about logarithms, and then I realised no. Just a classic bit of 2-star day. That is brilliant. Oh, I wish I had like the replay button so we could all re-experience how excited I was to talk about logarithms a little bit. Oh my goodness. How long has everyone been? How long did I spend or you spend preparing for maths? Cool question. We've been running these live streams for just a few weeks now, about a month, but I've only done about 4 or 5 of them. Yeah, area bounded by, yeah, we can talk about areas bounded by curve, the axes and some other line. I can talk about that. That's a thing. Do we have 2 curves on this sheet somewhere? A good trick I've seen sometimes is if you've got 2 functions, f of x and g of x, and you know that f of x is bigger than g of x, then the area like this is the integral of f of x minus g of x dx. Maybe this is a and b. And if you stare at the picture, it's kind of obvious why this is true after a while, I think. The first bit, the integral of f of x, would be the area underneath the top graph, which would include this bottom bit we don't want, but amazingly that's exactly the area underneath the bottom graph, which is the integral of g, which is why it's been subtracted. Good. And if you want to do a curve, the axes, and some other line, line's an example of another function, so I think it's a special case for this. Good. Good, right, okay. Could talk about it anyway. Oh, there's something really nice going on. It's in the extension for one of these sheets. I think the logarithm sheet talks about the integral of 1 over x. It does not talk about the integral of x, that's brilliant. I love that so much. Right, what a great sci-fi. I'm going to talk about a few of the warm-up problems. I'm going to pick a few that are my favourites, I think. If you want to see, maybe you've already tried the warm-up problems, maybe during the weird first half an hour of this live stream. If you want to talk about a particular one, then put the question number in chat. Oh, okay. That's a good question. There's a start question at the top. I don't really understand. Let's talk about that. While people are thinking about which warm-up questions they want, I'll add some to the list, by the way. I would like to talk about 11, and I would like to talk about 12. Which is just off the screen for you at the moment. But if you want to see what it is, you can get the worksheet on the website. Let's talk about why switching the limits. Yeah, so switching the limits around, there are 2 things that you might be interested in. Let's do some experiments. This is a terrible example. I'm going to go from 1 up to 2. Let's try and not pick one that's 0 if we're going to go and think about this. There we go. Okay. So if I do this integral, then I get 2 minus 1/2. 4 over 2 is 2 minus 1/2 is 3 over 2. Okay, but if I do this integral from 2 to 1, x dx, then I get x squared over 2 from 2 up to 1, which is 1/2 minus 4 over 2 is 2, which is negative 3 over 2. So I guess the reason that changing the limits around changes the sign of the answer is that when you do the integral, you're plugging in the limits the other way around. This is why you get a different answer. It doesn't change the actual area though. If you're interested in the area, let's try and draw that between 1, 2 and y equals x. If you want that area, then I think you probably want the first one, because you probably want a positive number. This is something you have to worry about though if instead of 1 and 2, it's numbers a and b, or some sort of something weird, because then you might not know for sure which one's bigger, and you might have to worry about the answer coming out to be negative or something, just because you happened to put them in. You didn't know, but you happened to put them in the wrong way around. I don't know how much that's quite abstract, right? But it's why I'm saying this is not necessarily the area, even if f's positive. Even if f's positive, because if a is bigger than b, then you've accidentally integrated backwards. Cool. Question 10 and question 11 aren't hard, but they are interesting. Let's vote for 10. Let's make James do 10. Interesting, same reason as 11. Yep. What's a good score on that? Have people pointed to the website? James always says 60. I sometimes say 70, I think. There's graph. Yeah. Graph. 12, 10. Why do people like the look of... Whoa, I missed this in chat. Jack, like the look of 10? Oh, that's an outlandish opinion, I think. I should probably ban that. Question 14 is, I think, a joke about how I can't number things very consistently. There's also a typo on this, and on the PDF. Sorry if you downloaded the PDF, this will get fixed at some point. I tried to update this question to the more cool and trendy number of 1729, but the update didn't stick. Right, we're not talking about any of the early ones. Michelle, the answer is probably no. I'll probably give you some marks if you follow the instructions in the question. And you've got 4 replies. Hopefully people, put your working out, says Prisma in the chat below. I'm going to skip all these ones. If you're doing A-level or equivalent, you've probably done a billion of these to work out turning points and things like that. 7 is really just checking that thing that I just said about B moving close to A and getting close to the tangent line. Integration is the opposite of differentiation. Right, cool. Let's talk about 10. So 10 is sort of a trick question in that something that it would be quite easy to sort of write this down. And this is true. I don't think I've made a mistake yet. 4, 5, 6, x is 7 over 7. But there's a slightly better approach, I suppose, but because loads of these terms turn out to be 0, and if we'd spotted that before, we could maybe have ignored them faster. I just had to do quite a bit of writing, and it's going to turn out that this one here, and oh my goodness, even my graphics tablet is having a 2-star day. These ones are all going to be 0, because when I plug in 1, I'm going to get the same thing as when I plug in -1, and they'll cancel out. So there's this general thing you should watch out for these odd powers of x integrated from -1 up to 1. It's a bit suspicious. Going back in here, once you actually plug in 1 and -1, I happen to know, I think this is helpful. I sort of sneakily used it a moment ago, that if it's just the sign changing, you get negative as the bottom one, so you add it on again. I don't really know what I'm thinking in my head, except maybe just I should put a factor of 2 on the top of each of these, 1 from the top, and then I kind of know -7 minus signs, 1 on the bottom. So then I've got some horrible addition to do, which I think is why people wanted to see me try and do this. 1729 is the smallest whole number that can be written as the sum of 2 cubes in 2 different ways. A fact that is often mentioned in a story about Ramanujan, which is really nice. I think people wanted to see me do this because I really struggle on the live stream about getting stuff like this right, especially if I try and talk at the same time. So I'm going to try and just, this is not for your education, this is for my entertainment, I'm afraid, to try and see if I can actually do all of this adding up at the same time as talking, because 15 times 7 is 70 plus 35 is 105. Something that I found really helpful when trying to do things like this is to just work really systematically to make sure I'm doing it the same every single time. 161, 176. I don't know, I think my brain likes repeating the motions as we go through. 340, 352 over 105. So that I'm always putting, I do my fractions all at once. Maybe that's slow, maybe I should be adding them in pairs and then adding them in pairs. If I was a computer, I would probably do it like that. But I'm not a computer. 140, 161, 176, stick, 34352. Woof! If people put there's some of the cubes in chat, yep. Somebody in chat has also put, 1729 has got its own Wikipedia page, which is very nice. Good, okay. So then this one down here was supposed to be a sort of the same joke, that you can do big powers. If you see an odd power integrated from -a to a, then you just get 0. Or if you really want to, it's 1730 divided by 1730. Pi minus pi, which is pi to the 1730 divided by 1730, take away pi to the negative pi to the 1730 over 1730, which, it's 0. Cool. For some value of cool. I sort of wanted to do these. This is my attempt to come up with things that look harder than they are. Ben sees pi over 4 because Ben knows an expression for pi over 4. Ben, can you remind me how that sum works? I sort of know what you mean. There's a sum with all these plus and minus signs in. And I sort of know what you mean. Yeah, how does it work though? It's got loads of plus and minus signs, and I think it's got odd numbers and it's got fractions, and it's pi over 4. Ben's going to put it in chat. Maybe. Who knows? These are, you can do all of these using different powers of x. But I thought I'd try and make them look a bit weird. This is x to the 1/3. This is x to the 30. I don't know, I thought it'd be fun to kind of just try and disguise it by factorising 30 to make you think about powers. This one is, I find these ones really hard to spot. Maybe you're great at them, but you can split up the fraction. It's a over this thing plus b over this thing, so you can split it into 2 terms. I find these just so hard to spot. I don't know why. I don't know what it is about splitting fractions up like this, because I know how to manipulate fractions. You just saw me add together some small fractions. Somehow I never think of breaking them down like that. And then over here, this one I put on the warm-ups as a sort of trap for people who know about integration by substitution. Sorry if I got you with my trap for integration by substitution, people. I think the best way is to just multiply it out and deal with it. If you multiply it out, you get 4 terms. They're all powers of x, and then just go and integrate all of them. And it's not that bad because it's just a small polynomial. I think I've multiplied out, right? So it's a test of a binomial thing at the same time. Thank you, Ben. Yes, that looks true. 1 minus a third plus a fifth minus a seventh plus ... It's pi over 4. I think that's true. Isn't that lovely? Brilliant. Mine didn't have any minus signs in, but I agree, it reminded me of that sequence too. Good. Thanks for looking up where the minus signs go. So I don't even feel like writing it all on the board. Let's do some more questions. I think we're doing quite well for time, despite the weird 20-minute section at the start where I tried to make a hard question harder and then solve it. To the dismay of everyone in chat. I think we're ready to do a couple more questions. This is a differentiation-based one. We're given a cubic, and like a lot of math questions, it's a cubic that's got a parameter in it. So we've got this k in here. It's got a turning point, and we're told the turning point is local minimum. This question is testing whether we know how to find turning points and whether we know about minimums. And I suppose later on whether we can solve equations. We're told that this turning point is at x equals 1. It's a little bit odd. Sometimes we're told to find where things are, and sometimes, like this time, we're asked to do something like this. I'm going to turn on a poll and read out some chat stuff. Can we prove that on stream? I sort of got distracted a little bit in the back of my head, and I thought I did quite well not getting too distracted by wondering whether I could adapt the thing that I'd written on the board to be a proof, because there's a power series that, now that I think about it, a power series that doesn't converge, or maybe it does converge. Yeah, the power series would work something like this. I think you can adapt the thing. This is not MAT, but I think you can expand this. Do a binomial series. So this is not MAT because at MAT you don't know how to expand this series. But I think it's this, right? At some point in A level, not for MAT, later on, or whenever you learn this expansion. I think I've got that right because it's a geometric series, right? Yeah, no, okay, this is MAT. Suddenly it's MAT. It's a geometric series with the common ratio minus x squared. 15 people have already done the MAT question that's underneath. You can integrate both sides of this, and on the left you get this integral, which you learn at, am I going to get away with this? I want to integrate it from 0 to 1, I think. At some point you learn that that's arctan of 1, which is pi by 4. At some point you learn that. And on the right, when you integrate things from 0 to 1, you get 1 minus a third plus 1/5 minus 1/7. We've proved it. Minus ... And that's why it's pi over 4, sort of. More than sort of. I think it's just wax. More behind the scenes. There's something slightly funny going on with some convergence and swapping the order of some summation and integration, but that's... there we go. Good, yeah, okay, so we can adapt the thing in the warm-up question to be a proof that pi over 4 has this lovely sum of the reciprocals of the odd numbers with alternating minus signs. Thanks for putting that in the live stream, Ben. That was a nice proof. I like the way that we got there by remembering a fact. Maybe that's the standard proof. Can I show why that integral is arctan? Not right now. Something school is very good at is teaching you things like why this integral is arctan. It doesn't look like arctan, right? It doesn't look anything like arctan. It's 1 over 1 plus x squared. Where's the pi? How could that possibly be pi over 4? Looks like this. It just comes down. It's not a circle. It just comes down. Like, that area is pi over 4, which is the same as a quarter circle, even though it starts just a bit wider than the circle and shorter at some points. Mad. Right, good. Yeah, it's the same area as a quarter circle. That's really weird. I sort of want to Desmos both of those. Let's Desmos them. People are doing a MAT question, right? This is a good use of everybody's time, because some people are doing the MAT question and some people are thinking about arctan integration. There's options of how you're engaging with the live stream. Is this irresponsible? Should I be just doing MAT questions in the MAT live stream? Here's 1 over 1 plus x squared. I'm going to try and get them both on screen at once. Okay, this is good. This is like split screen audience stuff. Yeah, so don't worry about this. This is 1 over 1 plus x squared, and this is square root of 1 minus x squared. I just want to show it between 0 and 1. And same for that one as same for this one as well. Right, cool. These functions are different. The red one is going to sort of carry on going down and tend down to 0. And weirdly, they have the same area underneath the curve. They just match up perfectly. This bit underneath here, in between, just perfectly compensates for this bit over here. They turn out to be there, yeah, both be pi over 4. Good. There's a question SV asked, do interviewers care much if you mess up basic maths at your interview? Under pressure, I always make mistakes in addition and stuff. SV, when I was in an interview, I tried to simplify the fraction 5 over 6. What was it? It's 5 to the power of 4 over 6 to the power of 4, and I tried to simplify that by crossing out the 4s to get 5 over 6. You know, same thing to the top and bottom, right? 5 over 6. Which was spotted by my interviewers, and they pointed out that it wasn't quite right, and then we found a different way to do the question. One of the nice things about interviews is, yes, you can make mistakes, and the mistakes don't last for as long as they do in exams. In an exam, you have to maybe spot your own mistake or find out when you get the marks back that you made a mistake. In an interview, hopefully someone lets you know straight away. Good. How are we doing on the voting? We having fun? The voting is 100%, by the way. If you have voted, I think you're correct. Like 30 people perfectly in perfect agreement. Should we do this question quickly? I might get a chance to do this question. Could we get a chance to do the question? Come on, people in chat. There's 30 people sitting in chat who have done this question. 33 people. And I've just told them they've all got the right answer. And statistically, I think that means that 3 of them, on average, probably, yeah, 3 of them are having a 1-star day and have just completely done a MAT question while I was messing around and doing something else. So if that's you and you were having that 1-star thing, then can we get you to like 1.2 stars with a target of 2 stars by the end of the thing? Is somebody going to vote for the wrong answer just to try and okay, right. There's this very good thing about what being funny means in hang on. Do I prefer Desmos over GeoGebra? I only know how to use Desmos. I used GeoGebra a bit about 15 years ago, and it was great then. And I don't think Desmos existed 15 years ago. I did some GeoGebra. I have not kept up with how to use GeoGebra, which sounds really bad. I just don't know how to use it. And Desmos, I used it very quickly in a hurry and have learned it as I went along. We're going to do the second derivative. Yeah, chat's telling me how to do the question. Brilliant. Harriet says, find the second derivative, set x to 1 and require that to be greater than 0 for a local minimum. Tony Wolf wants me to differentiate twice, do the second derivative, plug in x equals 1. Yeah, there's some recurring themes in chat. We're going to have a go at this. I think I'm going to write it out just so that we've got something written out. Shall I try and do two derivatives at once? Is that just showing off? It's a recipe for disaster, isn't it? I probably need the... No, okay, there's not. I thought that would be cool, but I've realised it's not cool. In a rare moment of self-reflection, I've realised that I should just do things the normal way. Right, cool, so let's do y by dx. I would like that to be 0, I think, at once. This to be 0 at x equals 1. I think that's true. Do I want that to be 0 when x is 1? Yes, I do. And it is, isn't it? Oh my goodness. Whoever wrote this question was very nice to us, because it just... If you plug in x equals 1, it all works. All the k's cancel, and all the numbers cancel. Just astonishing. Right, second derivative time. Okay, so there is a turning point. This is true. This is true. Yeah, it does have a turning point when x equals 1. Is it a local minimum, though? I see. So maybe this is a sort of trick answer over here. Because you could differentiate it and say, oh, brilliant, 0 derivative for all values of k. Let's just write that out. 3k minus 2k plus 1 plus 2 minus k. That's just equal to 0. The k's all get subtracted and the 2's... Yeah, anyway, cool. How nice. What am I doing? I'm going to subtract this. This is the second derivative. And copying everyone in chat, we want this to be a minimum, so we want this to be a positive thing at x equals 1. So that's going to be, we want 6k take away 2k plus 1 to be positive. We're going to do some careful inequality stuff. He says doing some uncareful inequality stuff because it's, there we go, I've got down to an answer. I've got down to C. There are now 48 people in chat with a 96% success rate. Well done, everyone. A couple of people went for E for that kind of trick answer of all values of k by not checking the second derivative. Sometimes it's a local maximum. Should we do a Desmos? Let's do a Desmos quickly. I've got a feeling that we have more time than questions, so I'm going to do a quick get Desmos. Minus k plus 1 x squared. Maybe you also did a Desmos sketch. Not an option in the exam, of course, but when you're practicing things, maybe it's nice to try things out with this sort of type the equation as a Desmos and move the sliders around. So here's the expression in the question. We can change the value of k, and there's always a turning point. Have I done this wrong? Done this wrong. There's always a turning point at x equals 1. You can see it moving up and down over there. But sometimes it's a minimum and sometimes it's a maximum. And the cutoff point is minus 0.5, I think. Or is it plus 1? Positive 0.5. Goodness me. Imagine what it would be like if I prepared these. There we go. It's kind of interesting at exactly 0.5, right? At exactly 0.5. I think it's... This is not relevant for doing the question, but at exactly 0.5, I think that is a turning point that is not a local... Sorry, I think that is a stationary value. A stationary point that is not a turning point, which is not a local minimum. Okay, good. I started writing at symbols instead of when or the word at. It's a bit weird, isn't it? Maybe I don't love it. Yeah, point of inflection. I love it when 3 people say the same thing at once. Brilliant. There we go. Let's put them on screen. Carl, names, and Kai. Good stuff. Okay. Where are we going? What are we doing next? Should we do another cubic with a K in it? We're pretty good at these, I think. Here's another cubic with a K in it. It's 2017. It's question 1A. Well, 1A, Brilliant. It's the other end of the spectrum from the kind of J question we tried earlier. Is it the same year? No. Other end of the spectrum. We're looking for real stationary, distinct real stationary points. Essentially, we want to know whether the cubic looks like this or whether it looks like this. I suppose these are the two options because it's got 2 out the front. It's a happy cubic that either increases or it does this, iconic cubic thing of going up and then down and then up again. Increasing, decreasing, increasing. These are ways that you might want to approach the question. Michelle's put a solution in chat. Thank you, Michelle. Let's do a vote as well. Voting is having that kind of structure. Oh, always good. Reflection, point of inflection. Sorry, laughing at chat. Good. There's a K in 2 different places in this one. I think it was in 2 or 3 places in the previous one. It's both got negative signs in front of the K's, which is. I wonder whether there's a. If we're going for sort of advanced strategy, and this is the sort of advanced strategy where it's possibly going to cause you to make errors. And people were really annoyed by this sort of thing before, but it's possibly an idea to write K is -2 times U. There's another U over there. And then the f of x thing is just 2 times x cubed plus x squared plus x plus 1. I don't know if that's helpful or not. I don't know if that helps you do something to the cubic, makes it easier to differentiate or not. Gets rid of all the minus signs, so that's quite nice. I've got to remember at the end, right? I've got to remember to put my U's in. Goodness me. Don't tell me in chat, don't tell me in chat. Was I fast enough? Yeah, okay. I think I was fast enough about fixing it. All the minus signs, plus signs now. So maybe I could work out whether that's got real stationary points. In terms of U though, which I'll have to remember that U is -1/2 K or something like that. Maybe this is a terrible idea. When I do my 2 derivatives, what do I want? I guess I want 1 derivative, right? I want this quadratic to have 2 distinct roots. Your algebra probably doesn't look like this because I've got some U's in. I want this to have like 2 roots. So I want b squared minus 4ac to be a positive number. So I want u squared to 3 to be bigger than 0. So I want, I guess, what is that? U is minus k over 2, so this is k squared over 4. Don't really feel like I'm getting to the right answer. Maybe that's a bad thing. Experimental, right? We're just experimenting right here. Something to do with k's and u's. And, oh, maybe I am going okay. U squared bigger than 3. When's u squared bigger than 3? That's not a hard question, is it? U squared is bigger than 3 when u is bigger than square root of 3, or u less than negative square root of 3. And u's. Oh, now I'm going to get a bit confused, aren't I? Because I've got my. Oh, now I'm going to get confused because my u's and my minus k's are going to mess things up around here. Cool. Right, I've discovered a confusing way to attempt this question, which suspiciously again involves bringing in a substituted expression in terms of u, and then everything gets a bit confusing and backwards. Let's have a look at what chat thinks. Chat overwhelmingly believes the answer to be B, which is 2 options. They want k to be either bigger than a big number or smaller than a very negative number. Let's find out if that's right by doing the question the sensible way, which is just to differentiate it and deal with the quadratic that you get. If you differentiate it, you get this quadratic. I'm in the sort of mood where I want to just sort of try out other weird approaches to doing questions, and we've had a couple so far and neither of them were good, but hey, we're learning. What do I want here? I've missed some factors of 2s and 6s possibly. Yeah, there's a 4 in here, isn't there? 4 times 2 to BC 4. Yeah, nice. Yeah, so I think this is k squared bigger than 12 then, isn't it? So we want k to be a big number. Yeah, cool. So I agree with chat. I think we want k to be bigger than the square root of 12 or smaller than negative the root of 12. 2 possibilities there because of how the k squared graph looks. Good stuff. Okay. It's not confusing until you make it to be confusing with a u. Brilliant. Can I just sub in u equals minus k over 2? I think I can actually. You know what? I think I just can. I think I can just plug this in over here, and then my confusing method would have given me the same thing. Ah. So I've got to decide, really, was it worth it? No. Right, good. Okay. The multiple choice questions seem easy to me, like this one, or almost impossible. I feel like this one was too easy in a way. I don't have stats on it, but it just feels like this being a bit too straightforward. Oh well, okay. Some of them are like that. Hopefully more experience. So I don't know if this one counts as. So who just said that some of them are easy and some of them are. It's got 5 thumbs up. It's an anonymous person, so I guess I'm talking to all the anonymous people. I think an important skill then is to be able to read the questions and decide whether you think it's going to be one of the ones you find easy or one of the ones you find difficult. So you have some idea about whether it's the sort of thing you might be coming back to or the sort of thing you might just quickly get done for a confidence boost of having done a question. Here it looks to me like I can see what to do with this question. There's a lot of reading to do. Which values of A? Fine, we've got some functions with A's in. So the area of the region bounded by the x-axis and the curve of y equals fx, bigger than the area of the region bounded by the x-axis and the curve of y equals g of x. So these are actually two very similar things. Let's put a bigger than. Let's put quote marks. Yeah, I'll put quote marks around this. Area of the region bigger than the area of the region. So there's this first area to do with f, and the second thing is to do with g. F and g are kind of not really interacting at all. They're just two separate areas I've been asked about. So I'm going to find the areas. I'm going to be careful. I'll find them in terms of a, and then I'm just going to compare those functions of a, right? So I think this is the sort of thing that you could get stuck into. Does that make sense? Thinks the question is too easy, so it makes it harder for himself. Yeah, obviously I'm quite keen to replace the 2 and the 4 with other powers, and we'll see which one wins in general. I've got a feeling that the winner will be the smaller power of A. Well, it depends on the value of A, right? But I reckon this wouldn't be too hard to generalise with powers of different numbers up there instead, because the plan is still the same, right? Thinking of the plan of what you're going to do is often the reason that the hard questions are hard. Here, maybe the plan is obvious. Maybe once you've read it, the plan of just do both integrals and compare the functions is really obvious. But if that was obvious to you, take a moment to reflect on how you came up with your plan, how you read it and you turned it into maths, and you worked out what you were being asked to do. I guess if I was putting it into words, I would say that recognising that these things, area of the region bounded by the x-axis, recognising that that's something you know about, that you can write down an integral, and that willingness to write down the integral, even without reading the rest of the question maybe, to just write down that integral is a good way to get stuck in. That sort of attitude will help you with the hardest questions as well, because if you can recognise anything and just write anything down, not knowing where it's going, then you can get stuck in. I think this question is hard to understand, but not that challenging to complete. Putting the different things in feels like a normal A-level question. Oh, that's an attack, right? So I think we're not going to do this one live. Actually, I'm going to take the point that some of these are too easy, and yeah, we're going to move on. I think it turns out to be the ones with 6s and 5s. So you can check on the solutions on the website to find out if I'm right. I just feel like it's 6s and 5s, but I can't quite remember if that's true. James seems like the kind of guy who'd eat pizza with a knife and fork. Some insight, Adam. Right, good. Okay. I love this live stream. Chat, I'm up to 3 stars. I'm having a good time. I'm up to 3 stars. We're going to try a long question. Although I feel now that I've picked out a long question that's maybe not hard enough. Maybe the theme of today's questions is integration questions that I've picked out that aren't hard enough. I don't know. That one with the integral of f of t seems pretty hard when I put it on the worksheet. Anyway, here's a question with quite a lot of reading and some integrals. So I feel like we should have a go at this one. It's a bit wordy, isn't it? If you mean this one. So let's have a go at this. This is obviously the best part of my job. Come on. I don't think you even really know what the other parts of my job are, but how could they be better than this part? We are asked to draw f of 1, f2 and f3. Oh, sorry, f subscript 1, f subscript 2, f subscript 3 of x. Okay, so they're functions of x, but they've got this subscript k, and this time it feels like they're positive whole numbers k, so this is just like a list of functions, like a sequence, or just different things going on. So what does this mean? F of 1 just means x to the 1 over 1, which is just x. I can draw that. There we go. F of x. But I'm going to label it f1 of x to show that I'm joining in with their notation. And then f2... Yeah, okay, it's just square root of x, isn't it? Where am I sketching these? It's going to go from 0, and then I know the square root of 1 is 1, so it's going to pass through 0.11. And then maybe I'm going to have to think a little bit for f3 of x, which is the cube root of x. The cube root is, I think, bigger than the square root for numbers between 0 and 1. It's very steep over here, and then it's very shallow and comes out underneath x squared after 1, 1. And I think that's all the intersection points. I wonder if I'm going to be asked in chat to prove this or something like that. Oh yes, interviews are online this year. Just glanced over at chat. Has Prism put this in chat as well? They are online. Someone else heard them. Yep. Prism says check the website, but also, yeah. It was the one with the 4s and 5s. Thank you, SV. Don't feel bad that I've called the questions easy. I'm in a weird mood where I want to make everything harder than it really is. If you've done any math questions today, you should be very proud of it. Because math is still a couple of months away, and these questions are genuine math questions. I didn't purposefully select them to set you up. Harriet can't see Prisma's messages. They are underneath. Prisma's putting things in replies underneath. If you're in Slido, you can click on somebody else's message, I think, and then view the replies. I hope you can see replies to other people's questions. Goodness knows. Maybe Prisma can reply to Harriet's question, and we'll see if that helps. Good. Right. Okay. What are we doing? I've just seen Denim's request in chat to use double integrals, which has snapped me back to the question to think, oh my goodness, why would we want to use double integrals on one of these? I don't want to do any double integrals on the mat. That sounds like making it harder than it needs to be. Yeah, Alfie has asked me why it's steeper for x to the 1/3. Thanks, Alfie. Good question. Let's have a look at what happens when we differentiate them. So think about steepness is the gradient. The gradient of that first one is 1/2 x to the minus 1/2, and the gradient of the second one is 1/3 x to the minus 2/3. And I've realised now this is not going to be very convincing about which one's steeper, because I'm now going to try and claim that x to the minus 2/3 is bigger than x to the minus 1/2 for small values of x, and perhaps that's not convincing at all. Maybe I should just be looking at the fraction, the difference, the fraction to compare these things. The f of 3 of x divided by f of 2 of x is equal to x to the 1/3 over x to the 1/2, which is x to the come on, x to the power of 1/6, which starts off, well, let's not think about 0 divided by 0, but between 0 and 1, x to the 1/6 is between, what am I doing? What is going on? X to the minus 1/6, come on. X to the minus 1/6, which is a decreasing function. It's bigger than 1 over here, and then it comes down, it goes through 1, and then it's smaller. And this is the ratio. It says that the top one is bigger, x to the 1/3 is bigger until you get to 1, and then it's smaller, which means it has to be steeper to start off with. Good, right, okay. There's people asking about double integrals, because they want to do exciting integration techniques to find these areas. I mean, if you know exciting integration techniques to find areas, then go for it. You can get the marks that way, that's allowed. Because any method gets you the marks if you're following all the instructions in the question. I don't want to do it with double integrals or sideways integration though. Yeah, thanks, x to the minus 1/6. Lewis, please could you do the mat in pen? The mat at the moment this year gets scanned in electronically, and it gets sent to markers electronically. So please please write in pen so that we can definitely, absolutely, 100% see. With pencil, we found that we sometimes can and sometimes can't, which means that it's just tricky. What do you get when you integrate a distance-time graph? You sort of phrase that like it's a joke. I don't know why that feels like a joke. It's not a joke, is it? What do you get when you integrate a distance-time graph? A distance-time graph? Oh, I see what they're asking for. Yeah, you get something that's meters times seconds. Yeah, good question. I don't know a name for that. Distance time. So if you sit around being far from home, you integrate your distance time thing and it just keeps getting bigger because you have a large distance for some time. What's that going to work out? I don't know what that's going to be for. Average of unsigned, average of signed. I don't know. Good question. I like it. I think I'm going to go. Oh, that's going to be. If you ask again next week, I might have a really good answer. That's brilliant. I should have more than 2 thumbs ups. Right, good. What are we doing? We're doing some integration. Oh, graphs. I think it's better to draw graphs in pencil. Yeah, bear in mind it's going to get scanned. I think there's an instruction on the front of the paper which says please use a pen, but every year lots of people ignore it. It's, to be honest, usually okay. But officially the instruction is to use pens. Deeps, says Jack, which is a comment on the philosophy of multiplying space and time together. It's very deep. But it's also speed backwards, which is good. It is not speed, because speed is meters per second, which would be the gradient of the distance time graph. The area would be distance times time. What is that quantity? I've got a funny feeling that it's not quite, no, it's nothing to do with energy, James. Oh, brilliant, love it. Right, good. Okay. Someone's put a very strange word in chat, which I think may be the solution, but it's maybe been moderated out. Right, good. Okay. If that was a technical term, then I'm sorry it got moderated out. Got caught by the filter. Oh my goodness, they have names. They have names. Somebody got caught by the auto filter, but then, anyway, never mind. Right, good. We're learning about physics in chat. I'm having a great time. What are we doing? We're doing part 2. It's the least focused we've ever been, and we've been pretty unfocused for the last month. Between the 2 points in I, where the intersection points, okay, the origin over here. Oh, spoilers that there are 2 points. Didn't say 2 up here, and now it says 2. Anyway, okay. If you labelled 3 intersection points, you'd be feeling a bit silly now. What is the area of the region between the graphs? Right, it is asking for the area between the graphs, that thing I foreshadowed earlier by mentioning that this could happen. What we want to do is the integral of x to the 1 over k plus 1, because that's f of k plus 1, take away x to the 1 over k dx, 0 up to 1. To find that area kind of between them, because I'm doing the area underneath the top one, take away the area underneath the bottom one. You can think of that as 2 separate integrals that have been subtracted if you like. In fact, that's how I'm going to do it, so maybe I should just be writing down 2 integrals, right? Big area, take away the area underneath the lower one. This turns out to be, I mean, it's not that hard to do, but it's not very illuminating to get on with it, so I think I'll let you do this one at home. Yeah, a basement, apparently. That's got through now. Okay. Good. So what's going on with this question? We have to find some area between these things. That's not too bad. You get some expression in terms of k, I suppose. The next part wants us to set c as a constant, where c is between 0 and 1. Find the x coordinates of the point of intersection between f of 1 and f of 2. And I think, yes, looking at these last 2 bits of question, f of 3 is now irrelevant to the question. It's all about x and square root x, which makes things nicer, because if this is c, then I suppose this y equals x graph. This is c squared, I think, because then the square root of c squared is c. Woof. Okay. Find the x coordinates. Okay, I'm done. There's c squared and c. And we want to make sure that the area between f1 and f2 is divided into 2 bits of equal area. So we've got, let's use some colours. we are asked to find the value of c such that this bit is the same size as this bit. Here's the bit of the question that's hard, I suppose. Some people in the chat want to invert it and to reflect. So there's this trick where you kind of integrate sideways. One way to think of it is you integrate with respect to y, but that feels a bit mad if you haven't seen it before, I suppose. The other way is to kind of reflect. If you reflect, then this square root curve, reflecting the line y equals x, this square root curve becomes a x squared curve, and the y equals x line becomes the y equals x line because I reflected in the y equals x line. If you do that, then the question is looking for the value of c over here that splits these things into equal regions. Let's put in the reflection, the things that we're looking for in the mirror. So people in the chat seem quite keen on this approach because once you've reflected, you're doing much more standard integrals. You're doing 1 take away x squared for that integral from 0 up to c, and you want that to be equal to the integral from c up to 1 minus x squared dx. If this looks like the sort of method that you wish you'd thought of, or the sort of method that you wish you knew how to do, there are some ingredients. You'll need to be able to work out how to reflect things in the y equals x line, which involves thinking about inverse functions, something to think about at home. And you'll need to be able to spot when to do it, which is sometimes if you've got horizontal lines, because then reflecting them in the y equals x line turns them into vertical lines. Vertical lines are much nicer. Okay, so if you want to do that, then you can go for it. Yeah, Michelle's approach though, in chat here, to think about triangles instead, I think that's a good approach. So there's a way to do this where you put in this little triangle down here. We already know an expression for the area between F2 and F1, so we just need to make sure the pink area is half of that, so we just need to find the pink area. If you split it up like this, you could do a triangle. Is this a triangle you were thinking about, Michelle? Maybe not. There are different choices of triangles. I can see a big triangle underneath as well. Maybe you're thinking about that triangle. X minus x squared. Oh yeah, x minus x squared. Thank you, thank you. One of those days. One of those days. Thanks, Nicholas. Yes, that triangle. Good. Yeah, cool. Works very well. You know the width of this triangle is c squared minus c. You know the height of this triangle is also c squared minus c. Because you know this point is c squared comma c squared. And this point is c squared comma c. Everything's fine. Everything's nice. You meant there's more than one. Okay. Yes, Ben. More on that in a second. More on this in a second. Okay, so we've got some integrals to do. So this way around we end up doing, we want the integral, so the pink region, we want root x minus x integrated from 0 up to c squared plus dx plus, and then this little triangle is 1/2 of c squared minus c all squared. We want that to be, 1/2 of the, I didn't work it out earlier, but was it in the question? Yeah, it was 1/6 for the area between F1 and F2. I think that's what we want to do. So this is maybe a more conventional approach to how to do this question. I'm just trying to skim ahead and think, does the c to the 4 term cancel out? Yes, it does. So the c to the 4 thing is going to cancel when you integrate this to get an x squared, plug in a c squared to get a c to the 4, but it'll be over 2 because when you integrate x, you get the factor of 2 down there. Over from squaring this bracket, we'll get a c to the 4 over 2, so the c to the 4s are going to cancel, giving us probably some really messy cubic. What sort of cubic am I going to get? Well, I want a cubic in C, so that's pretty good. This side, though, more obviously going to give me a cubic in C. Good. Ben's point. This reminds me of the other live stream with the floor of 2 to the x integral, which I think was actually last week. As one way Lewis said that you could think about the integral to the side instead. There was another way of, not quite an inverse function for that case, but another way of thinking about the other area, the bit above. Here that would be a bit like, instead of thinking about the pink area, trying to cleverly maybe think about this orange bit over here. Maybe this is what Lewis was doing in chat as well. Think about orange area under here and the big triangle. The big triangle kind of is a little bit irrelevant. I'm finding that area over there is not too bad because that orange area on the left is not too bad because the top of C, this is square root of x. You only have to integrate with one of you only have to deal with one of the functions. The x squared, the square root one over here. For this bit, it's just a big triangle, but that's like just integrating x. So maybe finding those orange regions is slightly easier than finding the 2 bits of pink region in between. But probably flipping it around and integrating the other way is much nicer. I think it was SV said something about volumes of revolution. Once you've learned about volumes of revolution, you're asked to do some integrals with respect to y, and yeah, maybe that does make you happier about integrating with respect to y. Good, okay. I've not really planned to have 2 live streams in a row where flipping the thing sideways was the best thing that we could do, but yeah, I don't mind it at all. I'm going to do the integrals on the board. Let's chat as well. Is it true that Oxford don't care about 4 A levels for maths? Yeah, a standard conditional offer is 3. Physics girl here for fun can answer this. It's always better to have 3 good marks than 4 mediocre. Yeah, so we don't use UCAS points is the thing. So if you've got 17 E's, then I don't really care how many UCAS points that is. Sorry. I don't even know if you can get 17 E's. Is that a thing? This is really nice, this method, isn't it? Because then these are just... I'm trying to do this one in my head to show off 1/2 and 1/3 is 1/6. And then there's a bottom limit as well, which is I need to subtract the c and add on over 2 and add on a c cubed over 3. Maybe I shouldn't have tried to do all that in my head. Multiply through by 6, and I'm going to get 2 times 2 is 4c cubed over here on this side. I'm going to get multiply through by 6. I'm going to get minus... This is going to look suspiciously like I'm just writing out the answer, isn't it? C over 2, I think minus 3c. I'm willing to negotiate on how many c's and things I get. I've got that many terms. Do I want all of these? Don't want all of these. Don't want that c term. Oh, it's not right. It's a c squared. Cool. And then it'll just add to that one. C squared 4s. Don't want that one. So minus c squared over minus c squared. Multiply through by 6. Do I want a 6 on there? Yeah, I did. Good. Right, cool. I should have just moved the c's onto the c squared when I spotted they were c squares instead of c's. When you get the paper, turn it sideways, then open the paper. Complicated. If I have further maths AS and not full A level, will that be considered? So if your school's not if your school doesn't teach further maths to full A level, then we look at the maths that is being taught to you. Hopefully your application says somewhere on it, I couldn't do further maths because my school doesn't teach it. Is that considered? Yeah, so then you're doing, the standard offer in that case, if we choose to make the offer, is A star in maths, AA and 2 other A levels, and A and AS for maths. Good. Durham accept the mat as well as their entrance. Good. What's the passing mark for the reduction? Ask Durham. The Durham question down here, it's just off the screen now. The Durham question, where is it? There it is. Accept mat as well. Was Durham admissions question. I don't work for Durham. I don't know how they decide. Nikita, the Top Rocks Maths was on the live stream on the Maths Club recently. If you go to the Maths Club website, you can find something like that. That is a question directed at Prisma. Okay. Ooh, kind of like a sector of a circle. Ooh, try a triangle to take the rest of square. I'm stalling for time a bit because I think we've run out of questions on the worksheet. I think that's the case. Yeah. Goodness me, we're going much faster now somehow, despite that first weird 20 minutes. I think it was not doing the middle question that was bad for me. Maybe to finish off over here, I'll do this. Oh, we haven't quite finished the question, have we? There's a sort of punchline at the bottom, hence find C. I don't know how you do this other than guessing the roots of the equation. It's a cubic equation. I don't know how you would find the roots other than guessing. Just guessing that C equals 1/2 works. Which is maybe what you would guess because it's in the middle. I think that works because 4 over 8 take away 6 over 4 plus 1. Yeah, maybe we could. I think extending the live stream from 1 hour to 2 hours was a very good idea. That yeah, we'll have to keep in mind for next year that maybe we need to put more questions on, and then we'll get into the problem of it being too many questions or something like that, and we'll be worried about doing too much or something. Can't really imagine that, to be honest. Minus 1/3, minus 4, add it on, multiply by 12 and get 4. I've got the wrong number of c squareds because I forgot to divide by 2. I forgot to subtract this one. Cool, good. Cubic. And do we need more? Oh, Prisma's trying to ask me something. Sorry. Hey Prisma, what's going on? Are you in Teams or something? What are you trying to ask me? I close Teams so that I don't get Teams messages during. Prisma, if you're trying to talk to me, do you want to put something in the chat moderation? Sorry, this is now a technical behind the scenes. Do you want to put something in the chat moderation panel and don't approve it? It's this sort of thing about, I think it's sort of guessing, but guessing is sort of a good approach for solving polynomials. We can do a little tangent if you like. Let's do a little tangent. Why am I guessing c equals 1/2? Maybe some people in the chat already know this, but there's some slightly helpful bit of theory for guessing fractions as the solutions to polynomials. Let's pull out this one. So this polynomial is 4c cubed minus 6c squared plus 1 equals 0. Let's imagine putting all of the fractions in. You know, we're mathematicians, we can do that. We can put in like p over q. So yeah, if we do that, it probably feels like we're making everything more complicated than it needs to be, but hey, maybe that's the theme of today. We get something like this. I've multiplied through by q cubed to make things look nicer. And observation from this bit, this term is a multiple of q, just gets a multiple of q cubed, and this term is a multiple of q. So this term must be a multiple of q as well. Now maybe p is a multiple of q. If p is a multiple of q, then no, just simplify the fraction until it's not. So let's put this in lowest terms. Let's put this in. Let's just plug in fractions that are in lowest terms. Let's say that p and q don't have any prime factors in common. So then this looks a bit suspicious. It looks a bit like maybe q's a factor of 4. Maybe something's going on there. We should think about 4s instead. So that's why I've tried fractions with the denominator 2 to start off with. There's something that you can look up. I think Ben's just put something in chat. It's called the rational root theorem. It's not on the MAT syllabus. It's slightly helpful, I suppose, in that it tells you what sort of fractions you can check. Here it's a good idea to check things that have 2 in the denominator. If the number up front was different, then different conclusion, I suppose. You can also point the other way and point at, hey, the first term's a multiple of p, middle term's a multiple of p, so maybe this is a multiple of p as well, but that's a bit suspicious, because if q is a multiple of p, I'll just simplify it. Hang on a minute. Hang on a minute. Good. Right, okay. Kind of like a segment of circle, don't think you could do that and subtract it. Yeah, you've got to be really careful with segments of circles, because circles have a very specific equation, and there's other equations that look a bit like it, other curves that look a bit like circles, but turn out to not quite be circles at all. So that's pretty bad. Live this hard for my best OMG clickbait face, which they're suggesting that I could use in the MAT live stream thumbnail. Yeah, so change of sign method. There's also change of sign methods. Also, if you're interested in this sort of thing, by the way, this is turning into a maths club for just like extra maths stuff. I think there's something called Descartes. Yeah, this is something to go and look up. Nothing to do with math. Similarly, you know, not entirely certain this is helpful for anything, but hey, it's true, and you can't say better than that. Descartes' rule of signs is something else you can get. It tells you that a polynomial might have some roots. What did you do for the fraction at the end there? What did I do for the fraction at the end there? I think I multiplied things by q cubed and then talked about things being around. Talked about p not being a multiple of q. Good, okay. I think we've run out of MAT stuff on integration. I'm actually going to do something I've never done before. I'm going to try and find another question. Because I feel like we've ended on quite a low note, perhaps, where really I wanted to end on a sort of triumphant high. So I'm going to try and find a question. Just bear with me 20 seconds here, sorry, while I try and load up a different past question for us to have a go at. Since we've got the time and we're here, problem is everyone was already left because you know, it got boring an hour ago. So only people who still around to get to do this extra integration question. Let's have a look at, oh no, I already did that one. This is more than 20 seconds. I've not stayed up to promises at all. 17, 18, 17. Don't like that one, don't like that one. That's the logarithms. Integral, yeah, let's use this one. Here we go. This is a triumphant finishing one. It's a J again. We started on a J question, but we're going to finish on a J question. It's one of those days. Look at this. So, importantly perhaps, this is an old question. I think it's using radians all the way through. If you don't know about radians, I would say just ignore this question. You'll learn about radians at some point in your life and you can come back and look at this. What I suppose you need to know is that these integrals are between 0 and 2 pi over here, because integrating between 0 and 2 pi is sort of in radian world how you integrate the entire range of cosine. Good. I did think about it, so yeah, we had this kind of plan that I was going to make up a math question. This is a plan for the logarithms one because I love logarithms. I was going to just make up a math question on the spot, and I had a little bit of thinking ahead of time, which is not very authentic, right? It's not very real. A little bit of thinking ahead of time about what the math question was going to be, and then I decided that it was a good idea and I should try and save it for an actual math question. So let's not do that. There is a real danger if I try and freestyle a math question, I end up coming up with one of the ones that I'm not allowed to tell you. Here's instead a math question from 2017. It's question J. We've got lots of different functions. It's sort of quite fun. It's not part of the question, but it's quite fun to imagine what these look like. Sine to the 100x. So sine, it goes between 0 and 1. Those are like small numbers, I guess, between 0 and 1. When you do small numbers between 0 and 1 to the power of 100, you get tiny numbers. So this function is something like, I can't draw on this. This function is something like 0 almost everywhere. I really don't expect this one to be the biggest. It's definitely smaller than pi. Yes, there's no radians anymore, which is why this question is not on the worksheet, because it's too annoying to convert it to radians. Let's try and get it into... Okay. See if this works. It's going to disappear. No, it's not. Open Paint, paste it in Paint. Good, there we go. Just going to try and get it into Miro so I can draw on it. This is top tier live stream now. We're now into the weird bit, beyond the first hour and a half. Let's try and get this in. If I was really clever, I would do this on the other screen. Let's have a go. Ha 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 ha. Brilliant stuff. People doing the question at the same time, right? So this is all very efficient. Don't upload that. Upload that. There we go. And then it uploads. And then we put it here, and then we zoom, and then we go back over here, we go to full screen, and now I can write on it. I'm very pleased with myself. Right, good. So as I was saying, this function over here looks, it's not part of the question to draw it, but it looks like this, 0, and then it's very suddenly 1, and then it's kind of 0 again, and then it's very suddenly 1, and then it's 0 again, and then it's very suddenly 1. It's kind of really, really tiny. It's an extremely small number. Which is a bit funny. Its actual value is definitely really close to 0. I don't want to work out what its actual value really is. But over here, we're going to do, all we're going to need to use for this question is between 0 and pi. Is that actually news? If we discovered news live on air, let's find out. Oh. What a weird way to learn that. Okay, everyone remember where you are. Weird. Right, cool. Okay. What is the UKMT? Yeah, there's a UKMT is going on as well. Physics go along with you. Yeah, because we're a live stream based in Britain, I'm going to go with what Chris says. That feels like the best thing to do. Just do a moment's silence. Wow, okay. Right, that was a strange thing to put into a live stream, but hey, let's do a maths question. So I think what we need for this question is that the value of this integral, signs between 0 and 1. So this is between 0 and pi. Should I stop? Is this going to be like a controversy if I keep going? I'm going to keep going. We're still going to ask the A-level questions, right? Is this just going to be like live stream clipped as like insensitive Oxford mathematician keeps going? You've got to worry about it, right? This one over here is entirely a negative function. Is it getting weirder that I'm switching between the talking out loud while also doing these things? So this integral is actually negative. So the only thing this had going for it is it was at least positive because the function that we're integrating is positive. So this one's larger than this e thing. Sine cubed minus 1, definitely negative. 108, irrelevant. This is very negative. Cool. Well, what else have we got going on? We've got this function over here. This one is kind of interesting. I've had this idea that we'll just bound them. We'll just say how big they are, which is quite an advanced idea, really, about bounding integrals. This one inside here, the thing inside the brackets goes between 1 and 3. When you cube it, because it goes between 1 and 27. 27 is huge. This feels quite large already. It's definitely bigger than 2 pi, because the thing that we're integrating is bigger than 1 all the way through. Over here, sine to the x positive x squared minus 2, I'm into a bit of a roll. I think this is a negative number, isn't it? So this is another negative integral. So I kind of eliminated 2 for just being negative numbers. What have we got left? Oh, this one's enormous, isn't it? Because 3 minus sine x, that's pretty big. That's bigger than 2. It might be equal to 2, but it's bigger than 2 for all x. So when I integrate it, I'm going to get something huge, because it's to the power of 6. So these numbers are massive. This is just the biggest by absolute far. This is bigger than 32 pi. This one now looks small to me. It is less than 27 times... Oh no, this hasn't worked out. Less than 27 times 2 pi. Oh, is this one not the biggest? It's bigger than 42. Have I got some numbers wrong? Take away 1, it's bigger than, if you take away 1, 2 to the 6, 2, 4, 8, 16, 32, 64. It's bigger than 64 pi. I can't do powers of 2. Good. And this is less than 54 pi. Okay, so this one is the biggest, I think. Good. Ooh, proof of irrationality of pi, using things a bit like this, different random integrals put together. Would Oxford prefer Fourier levels, is a question in there as well that an anonymous person asked me about 3 minutes ago. So if you've got the opportunity to do 4 A-levels, I personally think that that's a good thing to be doing, as long as it doesn't affect your grades, and so long as you can still meet the standard conditional offer, which is on 3 A-levels. If you have the chance, I would recommend you go for it, but we don't use it as an admissions criterion because, very professional, same criterion. We don't use it as an admissions criterion because not everybody's got the opportunity. It wouldn't be fair on the people at schools where you can only do 3 A-levels if we required you to do 4, or if we gave you an advantage for doing 4. It kind of tells me something about your school as well as telling me something about you. What about 5? There's Raphael, smiley face. If you've got the opportunity to do 5 A-levels, then that's a lot of learning. Yeah, right, good, okay. Do you want a quick intro of Fourier series transformations, a course that I'm teaching in 2023? Yeah, I guess maybe. They also involve lots of things where you get the sine of pi of x and cosine of pi of x, which I guess is why they've asked. It might be a helpful way to deal with sine to the 100. I think what I want to say instead is something about the way that we're bounding these integrals. It's sort of like realizing that, like the thing with the functions again. So realizing that this is some function that lives kind of up here between 2 and, what are the values on this function then? Lives somewhere between the minimum of this function is like 2 to the 6, 2 to 6, 64, and the biggest value it goes up to is actually huge. It goes up to 4 to the 6, which is incredibly massive. And it does something pretty wobbly and weird in between, but it's always between those two values. And kind of the power of this bounding method is to say, well, I don't care about all of this really complicated bit of the function. I can see that the area underneath includes the area underneath includes all of this bit underneath the line, because the function's above the line. So I don't really care about the top bit. I'm going to say that area is bigger than this area of the rectangle underneath, which is pretty good. Right, fourth A-level matter. If somebody has a conditional offer. If you have a conditional offer, it's a sort of legal agreement where your conditional offer might say you need to get A star in maths, A star in further maths, A in any third subject. If that's the legal text that you've been given and it doesn't mention a fourth A-level, then you don't need to get the fourth A-level to meet that conditional offer. Prisma's being really great. Well done, Prisma. We're going to wrap up in a little bit, I think. Request for Fourier series. Where do I even start? So chat, it turns out that you can combine functions together in a kind of similar way to how you mix paint colours together. Nobody really told me this at school. I think I knew that you can mix colours of paint together, and maybe you can play notes together in like a chord, and it kind of sounds good. And okay, fine, those are examples from music and art where you can combine things together. I guess I knew that you can use a prism or something to break down something complicated like light from the sun. You can break it down into its component parts. But I didn't know that you could do that for other things as well. So splitting things up is pretty powerful. Do you know what? It was a mad live stream before everything happened. It was mad in the first hour as well. That's what I'm going to remember. I'm going to remember where I was, and I'm going to remember that the live stream was already weird. Good. Okay. Advice on gap years. We can do it in a moment. We're doing Fourier series. You already know one sort of example of how to do this breakdown. I'm pretty bad at remembering how these formulas work, but I think, oh gosh, do you know something like, I'm going to get this wrong, I think. In the formula booklet, goodness me, in the formula booklet, there's something like cos of A plus B over 2, cos of, it's something like, it's something like this. Cos of A plus B over 2, cos of A minus B over 2. And on the right hand side there's like two functions added together or something. I can't quite remember how this works. It's something like this. There's something in the formula booklet that looks a bit like this, which is telling us, in a way, oh gosh, I should really look up this fact or something for your intro to Fourier series. This would be a lot more convincing if the brackets had terms in, right? Sometimes I think I'm just irritating enough to make you go and look things up properly. Do you know this in the formula booklet, right? I haven't got a formula booklet anywhere nearby. Oh goodness me. So yeah, further maths as well. So somewhere in there you learn a fact like this. But what it's really telling you, if you squint, is what I was going to do. I was going to write it out. I invite you to squint. Is that you've got some complicated function on the right hand side. That's a pretty weird shape actually. So this could be in general something like some wobbles, but bounded inside some other shape. Worth messing around with this. I'm imagining A and X. Oh gosh, I'm imagining a load of X's as well. Is the thing. But it's telling you that you can write it as the sum of two simple things. If you really read into the formula booklet, there's stuff like this in there. People are now looking at the formula booklet trying to work out what on earth I'm talking about. Let's work these out. I think this is further maths, or at least second half of A-level maths. It's not... ooh, yeah, okay. Jack, I'm going to work with that. Side tangent. This is... monumentally, this is the first double tangent. A tangent to a tangent. Now, tangents to tangents are not really a thing for the tangents that we know about, right? Because the tangent would just be a line, so the tangent to the tangent is the same line again. But weirdly, you can do, in higher dimensions, you can do a tangent to another tangent, which is an occult sort of technique that shouldn't really be encouraged. But here we are. You can differentiate twice, and that's like finding the derivative of your differential form, and then maybe you shouldn't be doing that. Anyway, what am I doing over here? I'm working out some other relationships. So this expression at the top, by the way, if you've never seen it before, it's brilliant. It's a thing for adding together. You can add together angles and find the cosine of the sum in terms of cosine and sine of the individual angles. So that's pretty great. And over here, we can also do, you can replace the b's with minus b's. People don't like that, do they? Replace the b's with minus b's. Or if you want to, replace the b's with minus c's and then replace the c's with b's. I feel like people aren't going to like that either. But really, I've just swapped the b's for minus b's. But this is fine, and then this sign is flipped over. That's kind of why it's true, and then it's been restated using the same 2 letters of the alphabet, which makes it look more mysterious than it really is. What am I doing? Oh yeah, okay, so if you add these together, this is a sort of function that looks quite nice. What on earth are we doing? What is going on? Okay, so this tells us that some product is the same thing as these. So I want, what do I want? Yeah, okay. I want to do the beats example, I think. Okay, let's get back over here. Yeah, okay, let's do the beats example, but put x's in. Let's put x's in. Yeah, so then this will be, the rule is that the producty thing, you need to add them and you need to subtract them. And then both cosines. Okay. Yeah, right, cool. Let's look at this in Desmos. Here we go. Prism's here. Yeah, sorry. Prisma's been trying to ask me a question for ages. Sorry, Prisma. It's just to double check that there are no marks for getting a multiple choice question wrong. No marks for working out in the multiple choice section. Sorry. I could have confirmed that faster. Sorry. Okay, right. Good example. Here we go. Cos a plus b over 2x times cos of a minus b over 2x. Okay. Give me some AB sliders. Perfect stuff. I love it. There we go. Isn't Desmos amazing? Look at this. So let's make that a bit thicker as well. So you sometimes have complicated functions like this, but look at it. It's lovely, isn't it? It's really good. This is the product of two different cosine waves, like this. So there's a sort of outside one. It's been multiplied by a different one. So in purple and in red, there are two different cosine waves, and they've been multiplied together, which gives this complicated black curve that's sometimes 0 and sometimes positive and sometimes negative. You can get a lot of weird stuff going on in here. If b is a very small number, is that what I want? I want b a very small number? Yeah, there we go. B is a very small number. Let's get rid of these. Then there's this sort of weird effect that this thing pulses on a very long wavelength, very long scale. So this is 3.5 over 2x and 3.3 over 2x. And you get this really long behavior like this coming out, which looks a bit mysterious, but it's actually just cos ax. I think this is what we just worked out, plus cos bx, or something like that, all over 2, maybe. Yeah, cool. That's a nice expression for what it is. It's just some sum of these cosine waves. Okay. So using A-level math stuff, there we go, got there. Using A-level math stuff, there are some cosine rules you learn that are really telling you how to break down complicated functions into expressions just using cosines. Amazing fact that we're not doing now. You can write any continuous periodic function as a sum of cosine waves. So using maybe lots of different cosine waves, you can write any periodic continuous function like that. Good. So in general, you could have something really complicated on the left, and you can always write it in terms of multiples. So there's this sort of sum that you write down to do. Maybe you need some cos x. Maybe you need some cos 2x. And then you add a little bit of green paint, and then a little bit of blue paint, and so on and so on and so on. And actually, maybe you just want a constant in the front as well. To like pick your function up a bit. But you can write any periodic. So this is any 2 pi periodic continuous function. Any 2π periodic continuous function, you can write like this, splitting it into its kind of spectrum of different cosine waves. Which is then great, because then you've kind of analysed it in terms of cosine waves. These tell you a little bit like looking at the notes in a chord. It's splitting down this complicated experience into different things. In fact, if you do this to the sound that you're getting from the notes in a chord, it's exactly what's going on, really, that splitting it down into the individual notes is what's going on. Good, right, okay. Choice of cosine, can you do the same thing with sine? Yeah, you can. True. Cosine and sine are pretty similar things, right? It'd be surprising if cosine was better than sine in some way, especially with that name. Yeah, you can do sine waves instead. They're good for odd functions. Oh, this is... Do I need it to be even? No, I don't. I've got 2's in. There's some different cases where you might want to use odd functions or even functions, depending on what you know about your original function. Cool, good. Did I say I had a third method for finding C? Yeah, I can't remember what I meant, but that sounds like the sort of thing I would say. So guessing, and then the rational root thing is good for having a more informed guesses, because then you can search on the allowed denominators to find rational roots. I think the third approach has got to be... Yeah, the third approach has got to be knowing the cubic formula, which nobody does. Let me know in chat if you know the cubic formula. But no, you don't. It's really complicated. But there is such a thing as the cubic formula. So you can take this cubic and write down the solutions using the cubic formula, which is like the quadratic formula, but worse, much worse. So yeah, that would be a third method for finding C. There we go. What a combination of methods. Guessing, number theory, insane theory. Good, right, cool. That Fourier thing was maybe the worst tangent I've ever done. And there have been a lot of tangents. So what happens if you ask for a tangent where I haven't really prepared? So we talk about the extension very quickly, because I've got you here for a minute. Is anybody still here? Oh my goodness, nobody's still here. Brilliant. It's just me. Ha, lovely. Okay, right. Hi, me. Here's a function that's a bit weird. Its integrals don't really converge. This doesn't sound like a big problem, but it's a really big problem for statistics. Where you can have quite a nicely behaved function. Like at the bottom here we've got this distribution 1 over x squared pi all over pi, which is a perfectly nice distribution really. I mean, you can sample from it. It gives you numbers back, and that's all right. The integral, you know, it has area 1, so it's a continuous probability distribution function. It's pretty nice like that. It just works. You can pick out numbers from it. But the expectation is undefined. It doesn't have an e of x. It doesn't have a mean, really, which is weird, especially because you can just take samples of it. You can set this up as a distribution and pull, get your computer to maybe generate random numbers according to this distribution, and your sample average doesn't settle down. I sort of thought it always would. Maybe that's naive, right? That if you have some distribution of some outcomes that could maybe happen, then it feels to me like there should be an average thing that could happen. There should be an average, right? You know, it should have an average of what you actually experience. But no, it doesn't. Occasionally, the thing that happens is not very often, but just often enough to matter. You get one really big number, and that stops the sample average from settling down towards 0. This is super weird, and I guess forces me to rethink kind of what I mean by average. So, something to think about maybe. On the other hand, its average is clearly 0. So clearly 0 because it's an even function. So it gives you even numbers just as often as it gives you odd. It gives you positive numbers just as often as it gives you negative numbers. So in some sense, it's obviously 0, but in a very practical sense, it's not defined. So that's the weirdest thing on this sheet, I think, and probably the weirdest thing in this weird 2 hours of my life. It's a calculus live stream. We should have expected tangents. There's the thing. Third method, Descartes' rule of science. That was, that was a tangent to a tangent again. That was not really a method. as much as, well, it's just a thing. Should we have a look at it? Should we learn what it is? We're going to really quickly learn Descartes' rule of science. I can never remember how this works, so I'm going to read it off here as well. Right, okay. Wikipedia is sometimes quite hard to read. Have you noticed this? It's just sometimes really hard to parse what it's trying to say. The rule states that if the non-zero terms of a single variable polynomial is the sort that we're dealing with. We've got just a variable x. Real coefficients, yeah, okay, so fine. The sort of polynomial you learn about in school are ordered by descending variable x. Okay, it's written in the normal way. So all of this bit means a sensible polynomial like the ones you see in school, written in the sensible way. Okay, non-zero terms of a polynomial, the number of positive roots is either equal to the number of sign changes between consecutive non-zero coefficients, number of positive roots. I guess they're just the positive roots, positive root section, positive roots. It's equal to the number of sign changes between consecutive non-zero coefficients. Okay, so look at that. Or, and this is the clincher, is less than it by an even number. And no technical note, root of multiplicity k is counted as k roots. Okay, right, there's a lot to take in. I think it's saying that you look at the sign changes in your polynomial. Where's our example polynomial? Here's our polynomial. So we've got two sign changes because we go from 4 to minus 6 to 1. We're ignoring a zero coefficient here. 4 to minus 6 to 1. We've got two sign changes. And Descartes' rule of science tells us that this either has two positive roots, or less than that by an even number. So either 2 or 0. Is that helpful information? Not really. If we haven't already solved for the c equals 1/2 root, it tells us, good news. This has either got 2 or no solutions. And given that we were told to find it, that sort of tells us that we will either be successful or not. Good. Descartes. Would Newton-Raphson here work to find c, says Rebel? My goodness. That's an exciting technique for finding roots. Newton-Raphson, I think I learnt this in school, but I think not everybody does. Newton-Raphson is a I think quite cool technique for finding roots of equations. Let's try and draw this cubic. I think it looks like this. What you do is you take a starting point, what Newton and Raphson do, I suppose. You take a starting point, starting guess, you find the tangent there, and you follow the tangent down to the x-axis. And that's your next guess for where the root is. And then you follow the tangent down to the x-axis, and that's your next guess for what the root is. And then you follow the tangent down, and you see it gets better and better. This picture is not super convincing, but hopefully it gets better and better as you spiral in there towards the root. If you do that, I think it will converge quickly, but you will never be given actually the number 1/2. Exactly. You'll be given lots and lots of very complicated fractions. You might notice that they're getting close to 1/2, and then write down 1/2. Yes, good. I'm sorry I didn't notice the Newton-Raphson. I'm sorry people have been putting Newton-Raphson in chat for ages. That is a good fourth technique. Good-ish. I mean, actually doing Newton-Raphson, actually calculating these tangents, the idea is your function is almost a straight line, so following the tangent should take you to the root. Actually calculating these tangents is really hard. Just starting value. And if you start too far away, it's just terrible. If you start over here and you follow this, you don't find it. You find the wrong root. You find the one over here. If you start over here, then I think it goes very, very negative. Possibly. There's this risk that it goes. Or maybe it converges in for that one as well. If you start over here, does it go converge miles over there? Goodness me. Right, cool. Newton-Raphson is a bit dangerous sometimes. If you start at this turning point, that's pretty bad, because then the tangent doesn't hit the x-axis at all. Good. I really want to do fast inverse square root. Fast inverse square root is brilliant. We're not doing it now, obviously. It's not the right time or place to talk about fast inverse square root. Possibly a Maths Club episode. Once MAT Livestream is all over, we do something called the Oxford Online Maths Club for the rest of the year, which is a lot more fun because we do lots of other stuff. If you get too far off, you can give you the wrong route, and it can also fail worse than that. Mames Junro has heroically put in chat, I think, yes, the description of how you find the next term, x subscript n+1 is equal to something to do with xn's. It's not that fast though. Not that fast to explain. It uses some sort of approximations to square roots as well. It's very good fun. I think I'm not allowed to show you the code, right? Because the code has at least one swear word in, and we're not allowed to swear on this live stream. There's the two rules of this live stream, right? Don't swear and don't divide by 0. And if you start Newton-Raphson at the wrong place, then the formula that was just on screen involved divided by f prime x, which is pretty bad. Cool. Jack's suggesting there to use the answer button on a calculator. You know, you don't get to use your calculator in a math exam, but yeah, you can write out, if you generate this formula, you can write out something on your calculator using the answer button, which would be a fun thing to do. There is a link in chat. Did it get approved or no? Or maybe it didn't get approved. Okay, there might be a link in chat to watch something about fast inverse square roots. We might talk about them in the more maths club at some point. I think it might have got moderated out. We might be. I'm going to refresh it. Okay. There's Raphael's put a link to people explaining fast inverse square roots, which is used in Quake. So that's Quake 3, I think. So it's very exciting. Okay, I think we're done. I think we did it. We talked about everything on the sheet, more or less. We didn't do many of the warm-up questions, but we're not going to do them now. Thanks for joining us in one of the weirdest MAT live streams. I promise they're not all like this. Most of them are quite a bit better than this. My name's James. I've been having a 2-star day. It went up to 3 stars and then I think back down to 2 stars. Next week, algebra. Oh, definitely loads of stuff to talk about algebra. And the week afterwards, polynomials. So 2 sort of even more pure mathematical stuff coming up there. We'll see you next week. Have a good week. We are somewhere between 2 and 3 stars. I hope you have a lovely evening. Goodbye. Blimey.